180 million years ago, two of the largest slabs of rock on this planet began colliding. The dinosaurs were still young, the Atlantic Ocean had barely begun to open, and in a stretch of the Pacific that no human being would ever see, something started that has not stopped since. One plate being driven beneath the other, forced downward into the interior of the Earth, with a pressure so immense it melts the rock it takes with it. That collision, running without pause for 180 million years, tore the ocean floor open into the deepest place on Earth, the Mariana Trench, nearly 7 miles from the surface to the bottom, so deep that the highest mountain on Earth would disappear into it with more than a mile of water still above the summit. And the collision has not finished. It is still happening right now at this moment, driving the trench deeper with every passing year. What began before the first flower ever bloomed on this planet is still quietly tearing the ocean floor apart beneath one of the most remote stretches of water on Earth. What that process actually does to the rock, to the water, to the structure of the ocean floor, and why this specific place became deeper than anywhere else on this planet, is a story that most people have never been told. In this journey, we go back to the beginning of it. Before we do, if you enjoy videos like this, please give this one a like and subscribe to the channel if you haven't already. The surface of the Earth appears steady at human speed. Mountain ranges hold their silhouettes against the sky for thousands of years. Continents seem fixed in place. Oceans return to the same shores generation after generation. Yet beneath that quiet stability, the planet is moving continuously, carrying entire sections of its outer skin across the globe with a slowness so immense it becomes almost impossible to notice. Far below the crust lies the mantle, a vast region of heated rock extending deep toward the core. It is not molten like a sea of magma, but neither is it permanently rigid. Under extreme pressure and temperature, the rock deforms gradually over immense spans of time, flowing in currents so slow that a single movement may take tens of millions of years to complete. The motion is silent and patient, hidden beneath the continents and oceans like the circulation of something alive. Resting above this mantle is the crust, the thin outer shell of the planet. It is fractured into enormous slabs called tectonic plates. Some carry continents thick with ancient granite and mountain roots. Others support only ocean floor buried beneath kilometers of seawater. Together they form a shifting mosaic that covers the Earth from pole to pole. These plates do not float on open liquid, but they are carried by the slow movement of the mantle beneath them, drifting a few centimeters each year through a process that never truly stops. There are two kinds of crust moving across the planet. Continental crust is thick, buoyant, and extraordinarily old. Some portions formed nearly 4 billion years ago and still survive today, preserved through countless geological eras. Oceanic crust is different. It is thinner, denser, and far younger. Almost none of it exceeds 200 million years in age. The reason is simple and relentless. Oceanic crust is constantly destroyed and replaced. Its journey begins along mid-ocean ridges, enormous volcanic mountain chains hidden beneath the sea. There, deep fractures in the crust allow heat from the mantle to rise upward. Molten rock wells out from below, cools on contact with seawater, and hardens into fresh basalt. New seafloor forms continuously in these submerged volcanic seams, spreading outward in both directions, year after year. The process resembles an immense conveyor carrying the ocean floor slowly away from its birthplace. At first, this young crust is warm and relatively light, but distance changes it. As the rock travels farther from the ridge, it cools gradually through the surrounding ocean. Cooling makes it contract. Contraction makes it denser. Over millions of years, the seafloor sinks lower, riding deeper beneath the surface as its weight steadily increases. Entire sections of the Pacific Ocean have been aging this way since long before mammals first appeared on land. The planet cannot continue creating crust forever without removing older portions somewhere else. The surface of the Earth is finite. Every new strip of seafloor born from the ridges begins a slow migration toward its eventual disappearance. Across the oceans, ancient slabs of cooled crust move steadily through darkness toward places where the planet folds inward and begins consuming its own surface again. Long before the trench existed, before the Pacific Ocean carried its modern shape, the surface of the planet belonged to a different geography entirely. Nearly every major landmass was joined together into the supercontinent Pangaea, a sprawling formation surrounded by a single immense ocean called Panthalassa. Its waters covered most of the Earth, stretching outward in every direction beneath skies unfamiliar to the modern world. In the early Jurassic period, around 190 million years ago, the Pacific Plate did not yet exist beneath those waters. The seafloor west of Pangaea was older then, arranged into other oceanic plates whose boundaries shifted slowly through Panthalassa like cracks moving through ice. Somewhere within that enormous ocean, three of those plates converged at a single unstable point known as a triple junction. These intersections are restless places even today, regions where stresses accumulate from several directions at once. In Panthalassa, the balance eventually failed. The crust fractured open. From deep below the seafloor, molten rock surged upward through the rupture in enormous quantities. Lava spilled continuously into the ancient ocean, cooling almost instantly against seawater and hardening into dark volcanic basalt. Layer by layer, new crust accumulated around the opening. What began as a narrow wound in the seafloor slowly expanded outward, forming a small triangular patch of fresh oceanic crust surrounded by far older terrain. This formation became the earliest Pacific Plate, still tiny against the scale of Panthalassa, but already beginning its long migration across the planet. Fragments of that original birth region still survive today. Geologists call it the Pacific Triangle, a section of ocean floor lying east of the Mariana region. The rock there is among the oldest intact oceanic crust remaining anywhere on Earth. It formed while giant reptiles still dominated the land, and long before grass, flowering trees, or modern birds existed. Most seafloor from that distant era has already vanished back into the mantle, erased through subduction over immense spans of geological time. The Pacific Triangle endured. As millions of years passed, the young Pacific Plate expanded steadily outward from its volcanic birthplace. New crust continued forming along spreading ridges, pushing the plate larger in every direction. The farther its edges traveled from the heat of formation, the more the rock cooled and thickened beneath the sea. Slowly, almost imperceptibly, the plate became heavier. The world surrounding it transformed as well. The Atlantic Ocean had not yet fully opened between the continents. North America remained connected to Europe. India had not collided with Asia. Antarctica supported forests along its coasts beneath a far warmer climate. Dinosaurs were only beginning to diversify into the immense variety of forms that would later dominate the planet. Through all of those changes, the Pacific Plate continued moving westward across the globe. Year after year, century after century, the motion remained too slow for any living creature to perceive. Yet over 190 million years, that silent movement carried an ancient slab of ocean floor toward a future already written into its own growing weight. Deep beneath the continents and oceans, far below the oldest stone ever touched by sunlight, The Earth releases heat left over from its formation billions of years ago. Some of that energy comes from the slow decay of radioactive elements hidden within the mantle. Some remains trapped from the violent collisions that built the young planet itself. None of it stays still. The interior of the Earth is constantly redistributing heat upward through rock that moves so gradually it appears motionless from the surface. Within the mantle, hotter material from deeper regions becomes slightly more buoyant and begins to rise. Over immense spans of time, it ascends toward the crust, spreads sideways beneath the plates, cools, and eventually sinks again into deeper layers. These circulation patterns are called mantle convection currents. They are not narrow streams or isolated rivers inside the Earth, but continent sized systems of movement unfolding across hundreds of millions of years. The plates above travel along with this motion, carried slowly across the globe by the restless mantle beneath them. Yet convection alone does not fully explain the speed and persistence of plate motion. Another force operates with greater influence, especially beneath the Pacific Ocean. As oceanic crust ages, it loses heat steadily into the surrounding sea. The rock contracts as it cools, becoming denser and heavier over time. Eventually, some portions become dense enough that gravity begins pulling them downward when they reach a subduction zone. This process is known as slab pull. The descending section of cold oceanic crust sinks into the mantle under its own weight, dragging the rest of the plate behind it. Once that descent begins, the force becomes enormous. A single slab can extend hundreds of kilometers downward into the earth, while still attached to the surface plate above. The motion resembles a curtain slowly slipping from a ledge under its own mass, except the material involved is solid rock many tens of kilometers thick. By the time the Pacific plate approached the western edge of the ocean basin, much of it had grown extremely old by oceanic standards. For nearly 200 million years, it had traveled outward from spreading ridges, cooling continuously in darkness beneath the sea. Its chemistry had changed with age. The minerals inside the crust and upper mantle became compacted and increasingly dense. The plate was preparing itself, silently and inevitably, for descent. Where a descending slab begins to angle downward into the mantle, the surface above responds. The seafloor flexes under the changing forces acting upon it. The outer edge bends downward, forming a long, narrow depression that deepens as the slab sinks farther beneath the neighboring plate. Over millions of years, that depression evolves into an ocean trench. The Mariana Trench formed through this slow mechanical process, not through sudden rupture or catastrophic collapse. Nothing exploded open beneath the Pacific. No impact carved the abyss. The trench emerged because the planet continuously recycles its surface, returning old oceanic crust back into the mantle from which it originally rose. The deepest place on Earth exists because the internal engine of the planet has been operating continuously for billions of years, patient and unbroken beneath the sea. Across the oceans of the Earth, long curved trenches mark the places where old seafloor disappears beneath neighboring plates. They arc along the Pacific margins, beside island chains, beneath cold northern waters, and along volcanic coastlines where the crust slowly folds inward. Many descend to extraordinary depths, yet one trench extends farther into the planet than all the others, not because of a single dramatic condition, but because several uncommon circumstances gathered together in the same place over immense spans of time. The first of those conditions began with age. By the time the Pacific plate approached the Mariana region, much of its crust had already existed for 170 to 180 million years. In geological terms, this is ancient for oceanic crust. Most seafloor is destroyed long before reaching such an age. Over that vast duration beneath cold ocean water, the plate steadily lost heat. The minerals within it compacted more tightly. The entire slab became denser and heavier than younger portions of the ocean floor elsewhere on Earth. Density changes the geometry of descent. Younger crust tends to sink at shallower angles because it remains warmer and more buoyant. The Pacific Plate near the Mariana boundary behaved differently. Its immense weight pulled it downward more steeply into the mantle, almost like stone slipping beneath fabric. As the slab angled sharply into the earth, the trench above deepened with it. Yet depth alone does not preserve a trench. Many trenches closer to continents gradually fill with sediment delivered by rivers over millions of years. Mud, sand, and pulverized rock drift downward through the water column, accumulating layer by layer along the trench floor. Some trenches become partially softened by this steady burial, their sharp relief muted beneath thick blankets of debris carried from nearby land masses. The Mariana Trench exists far from large continents and far from major river systems. No immense waterways empty nearby. Very little sediment reaches the trench compared to subduction zones bordering Asia or the Americas. The abyss therefore remained comparatively exposed, retaining the severe contours carved by the descending plate beneath it. Instead of being gradually buried, the trench stayed open and stark against the surrounding seafloor. A third condition emerged from the structure of the Pacific Plate itself. The crust approaching the Mariana region is cut by ancient fracture zones formed during earlier stages of seafloor spreading. These faults divided portions of the plate into elongated segments, creating a narrower section of crust entering the subduction zone. That geometry allowed the slab to flex downward more efficiently than at many other trenches, where broader sections of crust resist bending. The result was a particularly steep angle of descent. The seafloor folded inward with unusual sharpness, producing a trench deeper and narrower than nearly any comparable structure on Earth. The shape was not accidental. It emerged from the combined influence of ancient cooling, geographic isolation, and inherited fractures written into the plate long before it reached the Western Pacific. Remove any one of those conditions, and the Mariana Trench becomes less extreme. Together, they aligned with extraordinary precision, shaping a place where the planet bends farther inward than anywhere else beneath the ocean. Seen from orbit, the Pacific Ocean appears calm and uninterrupted, a continuous field of blue stretching across nearly half the planet. Yet beneath that surface, the crust approaching the Mariana region is undergoing slow deformation on a scale difficult to visualize. The Pacific Plate arriving at the trench is not a fragile layer of stone. It is an immense slab of cooled lithosphere, roughly 100 kilometers thick, composed of crust fused to rigid upper mantle beneath it. Bending something of that size requires forces operating over geological time. Before the plate angles downward into the trench, the seafloor first arches gently upward. This region is known as the outer rise, a broad swell formed as the leading edge of the plate flexes under increasing stress. On bathymetric maps, the rise appears subtle, almost easy to overlook beside the abyss farther west. Yet, it marks the beginning of one of the largest mechanical transformations occurring anywhere on Earth. Rock under enough strain eventually fractures, even deep beneath the ocean floor. As the Pacific Plate bends, networks of faults slice downward through the lithosphere. Some extend many kilometers into the slab, opening pathways that allow seawater to descend far below the seafloor. Water seeps into hot minerals buried within the crust and upper mantle, altering their chemistry atom by atom through reactions that unfold in darkness beneath immense pressure. One of the most important of these reactions is serpentinization, a process in which seawater transforms portions of mantle rock into new hydrated minerals. The stone itself changes structure, storing water within its crystal lattice. The descending plate, therefore, carries not only rock into the mantle, but enormous quantities of chemically bound water absorbed during its fracture and bending. Long before volcanoes rise nearby or unusual deep sea ecosystems appear above, these reactions have already begun deep inside the slab. The Pacific Plate currently descends beneath the Mariana region at roughly 2 to 3 centimeters each year. At human scale, this movement is nearly imperceptible, slower than fingernails growing. Yet, over more than 50 million years of continuous subduction, the cumulative distance becomes enormous. Vast sections of ancient ocean floor have already vanished beneath the trench, pulled downward into the mantle through uninterrupted motion spanning epochs. Unlike many other subduction zones, the slab beneath Mariana sinks at an unusually steep angle. Its exceptional density allows it to plunge almost vertically into the earth. Seismic imaging reveals the descending plate extending hundreds of kilometers downward through the mantle while still remaining colder and more rigid than the surrounding rock. Even at extraordinary depths, the slab continues to fracture under stress. These deep fractures generate earthquakes far below the surface, deeper than nearly any others on the planet. Some occur 600 or 700 kilometers beneath the Pacific. In 2004, an earthquake struck beneath the Mariana region at a depth of 751 kilometers. The rupture occurred so far underground that the epicenter lay deeper beneath the earth than the distance separating New York City from Chicago. The trench above remains only the visible expression of that descent. Far below the ocean floor, the plate continues folding downward into darkness, carrying seawater, minerals, and ancient crust slowly into the interior of the planet. For thousands of years, the deep ocean existed beyond measurement. Sailors crossed immense stretches of water while knowing almost nothing about what lay beneath their ships. Coastal shallows could be tested with weighted lines, but once vessels reached the open ocean, the seafloor disappeared into distances impossible to estimate. The water below became abstract, a dark, vertical space without visible end. Even maps reflected this uncertainty. Continents were drawn with increasing precision over centuries, yet the oceans between them remained largely blank beneath the surface. Mountain ranges on land could be climbed and measured, rivers could be traced from source to sea, but depth concealed itself completely. The ocean floor was hidden beneath pressure, darkness, and distance, inaccessible to every instrument available before the industrial age. In the 1870s, the British research vessel HMS Challenger departed on one of the first expeditions devoted entirely to scientific study of the oceans. Over nearly 4 years, the ship crossed thousands of miles of open sea collecting biological specimens, water temperatures, sediment samples, and depth measurements. The method for sounding the ocean was physically simple but painfully slow. Sailors lowered a weighted hemp rope over the side of the ship and carefully measured how much line disappeared into the water before the weight struck bottom. On March 23, 1875, the Challenger was southwest of the Mariana Islands, conducting another routine sounding in the Pacific. The crew released the line gradually into the sea. Hundreds of fathoms passed, then thousands. The rope continued descending far longer than expected, vanishing into the water with no sign of the seafloor below. Eventually, the line stopped at 4,475 fathoms, nearly 5 miles beneath the ship. The scientists aboard recorded the measurement carefully in their logs. They recognized the sounding as unusual. but they had no way to understand its full significance. The deepest place on Earth had been touched accidentally by a rope lowered from a drifting 19th century vessel. Decades passed before technology allowed more precise measurements. In 1951, another British vessel, HMS Challenger 2, returned to the region equipped with an echo sounder. Instead of relying on rope, the instrument sent pulses of sound downward through the ocean and measured how long the echoes took to return from the seafloor below. The readings confirmed an astonishing depth approaching 7 miles. The deepest known point in the trench was later named Challenger Deep in honor of both expeditions. Modern surveys refined the measurements further still. In 2021, precision pressure sensors and advanced sonar systems calculated a depth of approximately 10,935 meters, or 35,876 feet. Yet even these numbers are not perfectly fixed. Sediment shifts slowly across the trench floor. Underwater landslides reshape portions of the basin over time. Tiny changes continue beneath the ocean in darkness, beyond direct observation. Compared to the average ocean depth of roughly 12,100 feet, Challenger Deep descends to an entirely different scale. It is not merely deeper than the surrounding seafloor. It belongs to a vertical landscape so extreme that measuring it required humanity to invent entirely new ways of listening to the hidden shape of the planet beneath the sea. West of the trench, beyond the deepest water on Earth, another landscape rises invisibly through the Pacific. Peaks ascend from the seafloor, one after another in a curved chain stretching across the ocean basin. Most remain submerged beneath kilometers of water. Some climb high enough to break the surface, forming green volcanic islands surrounded by reefs and clouds. Their existence begins far below them, inside the descending slab, vanishing beneath the Mariana region. As the Pacific plate sinks deeper into the mantle, conditions surrounding the slab begin to change. Temperature increases steadily with depth. Pressure grows immense. Minerals formed long ago within the oceanic crust and upper mantle carry water locked inside their crystal structures, absorbed during the plate's long contact with seawater and altered further by deep chemical reactions during descent. At sufficient depth, those minerals become unstable. The water can no longer remain bound inside the rock. It is gradually released from the slab and forced upward into the mantle region lying above it, an area geologists call the mantle wedge. Although hidden completely beneath the surface, this transfer reshapes the geology of the entire region. Dry mantle rock requires extraordinary temperatures to melt. The addition of water changes that threshold. As fluids rise into the overlying mantle wedge, they lower the melting point of the surrounding rock through a process known as flux melting. Portions of the mantle begin to partially liquefy, even though the temperature alone would not normally be high enough to produce magma. The resulting melt is lighter than the solid rock surrounding it. Slowly, it begins to ascend through fractures and weaknesses in the crust above. Some magma cools underground, never reaching the seafloor. Some continues upward over immense periods of time, collecting within volcanic chambers beneath the Pacific. Eventually, pressure forces portions of that magma through the crust itself. Submarine volcanoes begin forming along a broad arc parallel to the trench. Layer after layer of erupted lava accumulates on the seafloor. Over hundreds of thousands of years, some volcanic peaks rise thousands of meters upward through the ocean. A few eventually emerge into sunlight and open air, becoming islands. The Mariana Islands exist because of this process. Guam, Saipan, Tinian, and the other islands of the arc are volcanic expressions of the same subduction system that created the trench beside them. Their mountains, valleys, and coastlines were built gradually from magma generated by the sinking Pacific plate far below the surface. The relationship between trench and island chain is deeply connected, though separated by roughly 200 kilometers of ocean. The trench marks the place where old crust bends downward into the mantle. The volcanic arc marks the region where altered mantle material rises back upward toward the surface again. One feature descends into darkness, while the other climbs toward open sky. Seen together, they reveal a continuous geological cycle operating beneath the Pacific. Ancient seafloor carrying seawater and minerals disappears beneath the trench, changes chemically under pressure, and eventually contributes to the creation of entirely new volcanic land. The Mariana Islands are not independent formations standing beside the abyss by chance. Both were shaped by the same slow planetary engine moving beneath the ocean floor for millions of years. Between the trench and the volcanic islands lies a quieter region of the seafloor known as the forearc. It does not rise sharply like the volcanic arc beside it, nor does it descend into abyssal depths like the trench itself. On maps, it appears comparatively subdued, a broad underwater zone suspended between descent and eruption. Yet beneath that calm topography, fluids are moving constantly through buried fractures in the crust. The Pacific plate does not sink into the mantle as a dry slab of stone. During its long journey across the ocean basin, seawater penetrated deep into faults and mineral structures within the crust. As the plate descends beneath the Mariana region, rising pressure and temperature begin forcing those fluids back out of the rock. Water, carbon dioxide, methane, and dissolved minerals are gradually squeezed upward through the overlying plate. These fluids do not rise evenly. They migrate through networks of fractures cutting across the forearc, searching for pathways toward lower pressure. Along certain regions of the seafloor, the material finally erupts outward in slow, persistent flows, carrying mud, altered rock fragments, and chemically unusual fluids from deep beneath the surface. The structures created by this process are known as serpentinite mud volcanoes. Despite the name, they differ greatly from ordinary volcanic mountains built by molten lava. These formations erupt cold slurry rather than magma. Thick mixtures of clay-rich sediment, crushed rock, and mineral-laden fluids ooze upward from below, spreading gradually across the seafloor over immense spans of time. Some of the largest Mariana mud volcanoes reach nearly 48 kilometers across and rise more than 2,500 meters above the surrounding ocean floor, dimensions comparable to major mountains on land. The chemistry of these eruptions is extraordinary. The expelled fluids are intensely alkaline, in some places reaching a pH of 12.5, similar to industrial bleach. Hydrogen and methane bubble upward through the vents, alongside minerals altered deep within the subducting slab. Many of these chemical conditions are rare anywhere else on Earth. The seafloor surrounding the vents becomes coated in pale mineral deposits produced through reactions between seawater and mantle-derived rock. Yet, even here, life establishes itself. Microbial communities thrive within the chemically active muds, feeding not on sunlight, but on reactions involving hydrogen, methane, and sulfur compounds. Around the vents, larger organisms gather as well. Clams anchor themselves in the sediment. Sea anemones sway slowly in the currents. Snails and corals inhabit regions saturated with fluids that would be toxic to most surface life. Entire ecosystems persist in an environment shaped almost entirely by geology rather than solar energy. Some researchers believe these serpentinite systems may resemble conditions present on the early Earth before complex life evolved. The interaction between seawater and mantle rock produces chemical gradients capable of supplying energy to primitive microbial systems. In laboratory studies, similar reactions generate simple organic compounds associated with prebiotic chemistry. The Mariana Forearc therefore preserves more than unusual geology. Hidden between the trench and the islands is a landscape where deep planetary processes create environments unlike almost anything else in the modern ocean. Places where chemistry, rock, water, and life remain tightly bound together beneath the Pacific in continuous slow motion. Not far from the Mariana Islands, beneath the Pacific surface where sunlight still fades into blue water, volcanic peaks rise from the seafloor in scattered chains. Some are dormant, others remain geologically active, releasing gases and heated fluids into the ocean through fractures hidden along their slopes. Among them stands Daikoku submarine volcano, one of the strangest volcanic environments ever observed on Earth. Near its summit lies a feature so unusual that, when researchers first documented it, there were almost no comparable locations known anywhere in the solar system. Inside a crater at approximately 410 meters depth rests a pool of molten sulfur, shimmering beneath seawater in perpetual chemical instability. Sulfur melts at 115 degrees Celsius. Maintaining it in liquid form on the ocean floor requires very specific conditions. The surrounding seawater exerts immense pressure, while the volcanic system beneath Daikoku continuously supplies heat and sulfur-rich gases upward through the crater. Measurements taken near the vent recorded temperatures exceeding 187 degrees Celsius, easily hot enough to keep sulfur molten despite the cold ocean surrounding it. The molten material collects within depressions near the vent field, forming dark yellow pools unlike ordinary lava lakes. Bubbles of volcanic gas rise constantly through the liquid sulfur, while mineral deposits accumulate around the crater walls. The environment remains chemically aggressive, saturated with acidic compounds released from deep volcanic fluids moving upward beneath the seafloor. Only one other known place in the solar system displays similar sulfur pools. On Io, one of Jupiter's moons, continuous volcanic eruptions spread molten sulfur across a landscape shaped by tidal heating and relentless geological activity. The comparison is striking because Io is among the most volcanically active worlds known. Yet, beneath the Pacific Ocean, part of that alien chemistry exists quietly on Earth. Nearby, another submarine volcano called Ifuku produces a phenomenon equally rare. At hydrothermal vents along its slopes, liquid carbon dioxide escapes directly from the sea floor. Not carbon dioxide gas, but liquid droplets formed under high pressure beneath the ocean. The vent fluids emerge at temperatures around 103 degrees Celsius, carrying dissolved gases upward through mineral chimneys. As the liquid carbon dioxide rises into colder seawater, it forms pale, shimmering clouds drifting through the ocean like inverted rainfall. Droplets ascend rather than fall, gathering into ghostly white plumes before dissolving into the surrounding water. No other confirmed site on Earth has displayed this exact process occurring naturally at such scale. These volcanic systems exist because the Mariana region combines extreme geological conditions within a relatively compact area. The descending Pacific plate delivers water and volatile compounds deep into the mantle. Magma generated above the slab interacts with sulfur-rich minerals and trapped gases under high pressure beneath the ocean floor. Heat chemistry, and tectonic movement remain tightly compressed together beneath the volcanic arc. The result is a landscape where ordinary assumptions about the seafloor begin to fail. Pools of molten sulfur persist underwater. Liquid carbon dioxide rises through hydrothermal vents. Mineral saturated fluids circulate continuously through volcanic rock beneath the Pacific. The Mariana subduction system does not simply produce depth, it produces environments shaped by combinations of temperature, chemistry, and pressure rarely encountered anywhere else on Earth. On maps of the Pacific Ocean, the Mariana Trench appears as a thin, curved line west of the islands that share its name. From space, it seems almost delicate, a narrow crescent drawn across an immense blue surface. Yet that line marks one of the largest topographic structures on Earth, a depression so vast that its true shape only emerged after decades of sonar mapping and deep ocean surveys. The trench extends roughly 1,580 miles across the western Pacific in a broad arc bending north to south. Its average width is about 43 miles, though the dimensions vary considerably along its length. Much of the trench already descends to extraordinary depths, but the deepest region lies near the southern end within a smaller feature called Challenger Deep. Rather than a circular pit, Challenger Deep resembles a narrow slot carved into the seafloor. It stretches for approximately 6 miles, while remaining less than a mile wide in some regions. The geometry is elongated and uneven, shaped by the bending and fracturing of the Pacific Plate beneath it. Even within this confined area, the abyss is not a single continuous chamber. Detailed bathymetric surveys revealed that Challenger Deep contains three separate basins known as the Eastern, Central, and Western pools. Low ridges divide them beneath the water. Subtle rises in terrain, separating depressions that each descend to extreme depths independently. The differences between the basins are measured in tens of meters, small variations relative to the enormous scale of the trench itself, yet enough to create distinct pockets within the deepest known section of the ocean floor. The terrain inside these basins is surprisingly complex. Early imagination often pictured the trench floor as flat and featureless, buried beneath still water and fine sediment. Modern sonar has shown something far more intricate. Terraces step downward along portions of the inner walls. Ancient carbonate platforms appear collapsed and broken along steep slopes. Sediment accumulates unevenly across the floor, constantly rearranged by underwater mass movement. Material does not remain still for long in such steep terrain. Submarine landslides periodically sweep debris downslope, carrying mud, fractured rock, and organic particles into deeper regions of the trench. These underwater avalanches reshape portions of the basin gradually over time, altering the contours of the seafloor in darkness beyond direct human observation. The inner walls themselves are severe. In some regions, they descend at angles steeper than nearly any exposed cliff on land. Certain sections plunge almost vertically for several thousand meters, forming immense underwater escarpments cut into the descending plate boundary. Pressure, seismic stress, and gravitational instability continuously influence these slopes beneath the Pacific. The trench also remains tectonically active. Small earthquakes occur regularly throughout the region as the Pacific Plate continues fracturing during descent. Some tremors ripple through the upper crust near the trench walls. Others originate far deeper beneath the seafloor within the sinking slab itself. Though invisible from above, the abyss is never entirely still. The Mariana Trench is therefore not a simple hole in the ocean floor. It is a constantly evolving geological landscape, folded, fractured, and reshaped by forces operating beneath the Pacific over millions of years. A moving structure hidden beneath kilometers of water and perpetual darkness. Water changes character as depth increases. Near the ocean surface, it moves freely with waves, storms, tides, and sunlight. Far below, beneath kilometers of descending water, the physical rules shaping the environment become increasingly severe. By the time the seafloor reaches Challenger Deep, the ocean is no longer simply deep. It has entered conditions unlike almost anywhere else on the planet. At sea level, Earth's atmosphere presses downward with a force defined as 1 atmosphere of pressure. Every 10 meters beneath the ocean adds roughly another atmosphere as the weight of water accumulates overhead. In shallow regions, this increase is manageable. Divers feel it in their ears and lungs within minutes, but pressure continues building relentlessly with depth. At nearly 11,000 meters below the Pacific surface, Challenger Deep experiences approximately 1,086 atmospheres of pressure, more than 15,750 pounds, press against every square inch of material at the bottom. Steel structures collapse under such force if not carefully engineered to withstand compression from every direction simultaneously. Even water itself changes under those conditions. A cubic centimeter at Challenger Deep is measurably denser than the same volume near the surface, compressed by nearly 5% beneath the immense weight above it. The ocean there behaves differently at the molecular level, shaped continuously by pressures that never relax. Simple objects reveal this compression dramatically. Researchers sometimes lower ordinary styrofoam cups attached to deep-sea equipment during trench expeditions. When recovered, the cups are no longer recognizable in size. They return compressed to the dimensions of small thimbles, their internal air spaces entirely collapsed by the surrounding water pressure. Nothing tears or shatters. The material simply contracts uniformly inward until it becomes compact and dense. Despite the geothermal heat rising from Earth's interior below the trench, the water temperature near the bottom remains between 1 and 4 degrees Celsius, only slightly above freezing. The enormous pressure alters how water behaves under cold conditions, preventing it from freezing solid despite the darkness and temperature. The trench floor, therefore, exists within a narrow thermal balance, cold enough to slow most biological processes, yet still entirely liquid. Sunlight disappears long before reaching those depths. Even clear ocean water absorbs light rapidly as depth increases. Red wavelengths vanish first, followed gradually by orange, yellow, and green. Beyond approximately 1,000 meters, no sunlight penetrates at all. Below that threshold begins permanent darkness, uninterrupted by day, season, or weather above the Pacific. Any visible light in the deep trench must therefore come from life itself. Some organisms generate brief flashes of blue bioluminescence through chemical reactions inside specialized cells. Tiny points of living light drift through the water column or flicker briefly across the seafloor before disappearing again into darkness. Sound behaves differently as well. Increased pressure affects the speed at which acoustic waves travel through seawater. Deep within the ocean exists a region known as the SOFAR channel, where temperature and pressure conditions allow sound to move extraordinary distances with minimal energy loss. Low-frequency signals produced in one region of the Pacific can travel thousands of miles through this hidden acoustic layer. The trench is therefore shaped not only by geology, but by a complete transformation of physical conditions. Pressure, cold, darkness, and sound combined there into an environment operating according to rules profoundly different from the familiar surface world above. For decades after the trench was first measured, its deepest regions remained entirely beyond human reach. Soundings and sonar profiles revealed depth, but depth alone was abstract, numbers written onto maps without direct witness. No person had descended into that darkness. No machine carrying human passengers had ever endured pressure on such a scale. The bottom of Challenger Deep remained physically real, yet almost unreachable, in practical terms, separated from the surface by nearly 11 kilometers of crushing ocean. The vessel built to attempt the descent looked unlike ordinary submarines. Called the Trieste, it belonged to a class of deep diving craft known as bathyscaphes, vehicles engineered not for horizontal travel, but for vertical movement into the deep sea. Its design reflected the strange demands of the abyss. Above hung a massive float filled with gasoline, chosen because gasoline is lighter than water and remains compressible under pressure far better than air. Beneath the float was suspended a small steel sphere containing the crew. That sphere was the true heart of the craft. Its walls measured approximately 5 inches thick, forged from specially treated steel, capable of resisting pressures that would instantly collapse conventional submarines. Inside, there was little space to move. Two men sat surrounded by instruments, batteries, and the narrow porthole through which they would eventually observe the trench floor. On January 23, 1960, Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh sealed themselves inside the pressure sphere and began descending into the Pacific. The journey downward lasted nearly 5 hours. As the bathyscaphe sank, sunlight disappeared above them, layer by layer, until the ocean outside became completely black. The descent remained tense even before reaching maximum depth. At approximately 30,000 feet, one of the outer plexiglass observation windows cracked with a sudden sharp sound that echoed through the vessel. In ordinary conditions, such damage might have ended the mission immediately. Yet the cracked component was not part of the pressure hull itself. Piccard and Walsh examined their instruments carefully, confirmed the steel sphere remained intact, and continued downward into deeper water. Outside the vessel, pressure increased continuously with every meter descended. By the time the Trieste approached the trench floor, more than 1,000 atmospheres pressed inward against the sphere from all directions. The bathyscaphe moved slowly through darkness, broken only by drifting particles illuminated in its exterior lights. Finally, at a recorded depth of approximately 35,797 feet, the Trieste settled onto the bottom of Challenger Deep. Sediment stirred upward around the craft in pale clouds, reducing visibility through the small viewing port. Yet within the illuminated water near the seafloor, the two explorers observed movement. Piccard later described seeing what appeared to be a flatfish crossing the sediment. The report became famous because vertebrate life, surviving under such pressure, challenged assumptions about the limits of biology. Later researchers questioned the identification, suggesting the animal may instead have been a sea cucumber or another invertebrate shaped by the drifting sediment. But uncertainty did not diminish the significance of the moment. For the first time in human history, living creatures had been directly observed at the deepest known point on Earth by human eyes resting on the floor of the Pacific abyss. The Trieste remained on the floor of Challenger Deep for only 20 minutes. After nearly 5 hours descending through darkness, the time spent at the bottom passed quickly inside the small steel sphere. Every system aboard the vessel operated under immense stress, and the ascent back toward the Pacific surface would itself require several more hours. Yet within that brief window, Pickard and Walsh became the first human beings to directly observe the deepest known environment on Earth. Outside the porthole, the trench floor did not resemble the jagged volcanic landscape some scientists had imagined. Instead, the seafloor appeared pale and soft, covered in fine sediment that reflected the vessel's exterior lights in muted shades of white and gray. The material consisted largely of microscopic remains, drifting downward from distant surface waters above. The accumulated shells and skeletal fragments of plankton slowly settling through the ocean over immense spans of time. At those depths, even the quiet fall of organic particles becomes part of the geology. The trench floor gathers material continuously from the upper ocean, preserving a slow rain of biological debris compressed beneath enormous pressure. Visibility around the vessel remained poor. As the Trieste settled onto the bottom, turbulence from its descent disturbed the fine sediment and lifted clouds of particles into the surrounding water. The vessel's lights illuminated only a narrow circle, extending outward from the porthole before fading into suspended haze and darkness. Beyond that small cone of light, the trench disappeared completely. The limitations of the expedition were significant. The bathyscaphe had not been designed as a sophisticated research platform. It carried no robotic arms, no sediment corers, no collection chambers, and no instruments capable of retrieving biological samples from the seafloor. The mission's primary objective was survival itself. Engineers and naval planners needed to know whether a human-occupied vessel could physically withstand pressures exceeding 1,000 atmospheres. Inside the sphere, Pickard and Walsh recorded observations carefully while monitoring the integrity of the craft. Every sound within the hull mattered. At such pressures, even minor structural failure would have been catastrophic. Yet the steel chamber endured, proving that human engineering could survive conditions once thought nearly impossible to reach alive. The observation of possible animal life became the most discussed moment of the expedition. Through drifting sediment near the seafloor, Pickard reported seeing what appeared to be a flatfish moving slowly across the bottom. Later scientific analysis questioned the identification because fish anatomy at such pressures presents significant biological challenges. Some researchers suggested the organism may instead have been a holothurian, a type of sea cucumber capable of surviving extreme deep-sea conditions. Regardless of the exact species observed, the larger conclusion remained unchanged. The trench floor was not sterile. Biological activity existed even beneath nearly 11 kilometers of water in permanent darkness and under crushing pressure. After resurfacing, much of the expedition's technical information entered military classification under the United States Navy. Full scientific details were not immediately released publicly, and for years the deepest crewed descent in history remained partly obscured behind official secrecy. Yet the significance of the dive continued spreading quietly through oceanography and engineering alike. For the first time, the deepest region of the Pacific had shifted from abstraction into witnessed reality, a place not merely measured by instruments, but briefly seen by human eyes through a small window beneath the sea. After the Trieste surfaced in 1960, the deepest known point on Earth fell silent again. No crewed expedition followed. No second descent arrived months later to continue the work. Decades passed while Challenger Deep remained almost entirely untouched by direct human exploration, existing at the edge of scientific knowledge like a place briefly visited and then abandoned. The absence was not caused by indifference. Oceanographers, engineers, and naval researchers all understood the significance of the trench. The difficulty lay in the brutal engineering demands required to return there safely. Every component of a deep diving craft had to survive pressure strong enough to deform metal, shatter ordinary glass, and collapse hollow structures instantly. Even tiny imperfections in welds or seals could become catastrophic under more than 1,000 atmospheres of compression. Materials science during the 1960s remained limited compared to later decades. Precision machining capable of producing perfectly reliable pressure hulls at extreme tolerances was enormously expensive and technologically difficult. The Trieste itself had been an extraordinary achievement, but replicating or improving upon that success required financial and industrial resources. Few organizations were willing to commit for purely scientific exploration. Space exploration, meanwhile, captured global attention. Rockets, satellites, and lunar missions unfolded publicly beneath bright skies, while the deep ocean remained hidden beneath kilometers of water. The abyss offered no dramatic horizon visible to television audiences. Yet, in terms of environmental hostility, Challenger Deep rivaled the most extreme regions ever visited by humans. In the decades following the Trieste expedition, robotic technology slowly advanced enough to continue exploring the trench indirectly. Unmanned probes could tolerate risks that crewed vehicles could not. They carried cameras, sensors, and sample collection systems into depths too dangerous for routine human descent. In 1995, the Japanese robotic vehicle Kaiko successfully reached Challenger Deep and retrieved sediment samples from the seafloor. Within those samples, researchers confirmed microbial life living inside the trench mud itself, organisms surviving under conditions once assumed nearly incompatible with biology. Kaiko expanded scientific understanding of the hadal environment while operating entirely through remote control from the surface far above. Other robotic systems followed. Among the most advanced was the United States vehicle Nereus, designed specifically for extreme depth exploration. In 2009, it descended successfully into Challenger Deep, collecting geological samples and imaging portions of the trench floor with far greater detail than earlier expeditions had achieved. Yet, even advanced machines remained vulnerable there. During a later dive in 2014, Nereus was lost at depth. Investigators concluded the vehicle likely imploded under pressure during operations in the Kermadec Trench. Communications ceased suddenly, and debris later surfaced in the Pacific. The destruction served as another reminder that the deep ocean remained mechanically unforgiving even to sophisticated modern technology. The span between 1960 and 2012 therefore became one of the longest interruptions in the history of major human exploration. More than half a century separated the first crewed descent from the next. During that time, humanity orbited Earth, landed astronauts on the moon, built permanent space stations, and explored planets with robotic probes, while the deepest region of Earth's own ocean remained largely inaccessible. For 52 years, Challenger Deep existed in a strange state between discovery and isolation, measured, mapped, known to contain life, yet still beyond the practical reach of almost every human being alive. More than half a century after the Trieste vanished into the Pacific darkness, another vessel descended toward Challenger Deep, carrying a single human occupant. The ocean above remained unchanged in appearance, waves and sunlight moving across the surface as they always had. Yet far below waited a landscape almost no person had ever seen directly. This time, the descent would not occur inside a slow steel bathyscaphe suspended beneath gasoline floats. Technology had changed, materials had changed, the abyss itself had not. On March 26th, 2012, filmmaker and explorer James Cameron began his solo descent aboard the Deep Sea Challenger, a vertically oriented submersible engineered specifically for rapid movement into extreme depths. Long and narrow in shape, the craft resembled a mechanical spear descending point first through the Pacific water column. The vehicle measured approximately 7.3 meters in length and weighed around 11 tons. Near its base sat the pilot sphere, a cramped compartment only 109 centimeters in diameter. Cameron remained folded inside the chamber for the duration of the expedition, surrounded by controls, monitors, batteries, and life support systems packed tightly within the confined space. Unlike earlier dives that required many hours to reach the trench floor, the Deep Sea Challenger descended rapidly. In roughly 70 minutes, the vessel traveled nearly 11 kilometers downward through successive layers of darkening ocean until it approached the floor of Challenger Deep. Cameron ultimately reached a depth of approximately 35,787 feet, only slightly shallower than the record established by the Trieste in 1960. The descent itself passed through complete darkness, interrupted only by the submersible's external lights and drifting marine particles suspended in the water. At such depths, the surrounding ocean presses inward continuously with forces strong enough to deform metal structures if even minor weaknesses exist. Every seal, electrical connection, and structural component aboard the craft functioned under conditions impossible to reproduce fully at the surface. Once on the seafloor, Cameron remained below for more than 3 hours, far longer than the brief stay achieved during the Trieste expedition. The submersible carried advanced imaging systems, sediment sampling tools, and robotic equipment designed to operate within the hadal environment. High-resolution cameras captured the trench floor in stereoscopic detail, while robotic arms attempted to collect geological and biological samples from the sediment. The seafloor itself appeared sparse yet active. Fine sediment stretched outward in pale rippled fields broken occasionally by scattered rocky outcrops. Tiny organisms moved across the mud beneath the vehicle lights, subtle motion visible against the otherwise still landscape. Marine particles drifted downward continuously from the distant upper ocean, creating what Cameron later described as a slow snowfall descending through the water column from the illuminated world above. Not every system functioned perfectly. A hydraulic malfunction affected the robotic arm during operations on the bottom, limiting the amount of material that could be collected during the dive. Even with decades of technological advancement, the trench continued imposing severe constraints on machinery operating under extreme pressure. After resurfacing, Cameron described the environment as alien, isolated, and unlike any ordinary terrestrial landscape. In measurable physical terms, he was correct. Challenger Deep combines pressures, darkness, temperature, and isolation into conditions closer to those imagined for distant planetary oceans than to familiar environments on Earth's surface. By the late 2010s, deep ocean exploration had entered a new phase. Advances in metallurgy, syntactic foams, pressure-tolerant electronics, and navigation systems gradually transformed the hadal zone from a destination reached only once in a generation into a place that could, with enough resources and engineering precision, be visited repeatedly. Challenger Deep still remained among the harshest environments on Earth, but the technology to reach it was no longer experimental in the same fragile way it had been during earlier decades. Retired United States Navy officer and explorer Victor Vescovo organized an ambitious project known as the Five Deeps Expedition, a mission intended to visit the deepest point in each of Earth's five oceans. At the center of the expedition was a submersible called DSV Limiting Factor, constructed specifically for repeated operations at full ocean depth. Unlike earlier deep diving craft designed for only a small number of descents, the limiting factor was engineered for reliability and reuse under extreme pressure. Its spherical pressure hull was built from titanium, a metal combining exceptional strength with comparatively low weight and strong corrosion resistance in seawater. The hull underwent testing beyond the pressures expected at Challenger Deep before any crewed dives began. On April 28, 2019, Vescovo descended into the Mariana Trench and reached approximately 35,853 feet beneath the Pacific surface. The dive exceeded the modern depth record set during the Deep Sea Challenger expedition and became the deepest, verified crewed descent ever completed. What distinguished the expedition further was repetition. Vescovo returned to Challenger Deep again on May 1st, and then again afterward. In total, he completed 4 separate dives into the trench, more visits than any other individual had ever made to the deepest known location on Earth. The abyss, once accessible only through isolated historic descents, had become a place reached repeatedly within a single expedition. The seafloor itself appeared quiet beneath the submersible lights, pale sediment stretching across the basin floor in subtle ridges and depressions shaped by currents and underwater mass movement. Small organisms moved through the mud, while marine particles drifted continuously downward through the water column from the distant upper ocean. Yet, among the sediment, another presence appeared. During the dives, Vescovo observed debris resting on the trench floor, including what appeared to be a plastic bag and fragments resembling discarded food packaging. Later scientific analysis of sediment samples collected from Challenger Deep confirmed the presence of microplastics distributed throughout the mud itself. Tiny synthetic particles had become incorporated into one of the most isolated geological environments on the planet. The pathway downward was indirect but persistent. Plastic entering the ocean at the surface gradually fragments into smaller pieces through sunlight, abrasion, and chemical weathering. Organisms colonize the material, increasing its density until it slowly sinks through the water column over years or decades. Ocean trenches act as natural accumulation zones where fine material settles and remains trapped within deep basins. The discovery altered the emotional geography of the trench. Challenger Deep had once symbolized remoteness beyond ordinary human reach, a place separated from civilization by immense depth and pressure. Yet industrial material from the surface world had arrived there rapidly within the span of a few human generations. A geological structure formed over 180 million years now contained traces of disposable objects designed to exist for only moments in human hands. Seen from orbit, the Pacific Ocean appears calm, an immense blue surface spanning nearly half the planet. Yet around its edges runs a fractured boundary where continents rise, volcanoes burn, and ocean floor vanishes back into the earth. The Mariana Trench belongs to that boundary, not as an isolated scar, but as one segment in a continuous planetary system operating across tens of thousands of kilometers. Geologists call this system the Ring of Fire, a vast arc tracing the margins of the Pacific Plate and the smaller plates surrounding it. Stretching roughly 40,000 kilometers, it contains close to 3/4 of Earth's active volcanoes and produces the overwhelming majority of the planet's earthquakes. Beneath the mountains, islands, and coastlines of the Pacific Basin, tectonic plates are colliding in slow motion, carrying entire regions gradually downward into the mantle. The Mariana Trench marks one of those collision zones. Far below the western Pacific, the Pacific Plate descends beneath the smaller Mariana Plate, continuing a process that has operated for tens of millions of years. The trench is the deepest expression of subduction on Earth, but the underlying mechanism is shared across much of the Pacific world. Northward, similar forces shaped the Aleutian Arc, stretching from Alaska into the Northern Ocean, where volcanic islands rise from another descending slab of seafloor. Farther south and west, the Philippine Trench and the Japanese Island Arc emerged through related interactions between converging plates. Across the eastern Pacific margin, subduction lifted and compressed the Andes of South America, building mountains thousands of kilometers long through immense geological pressure sustained over deep time. Though separated by oceans and continents, these regions remain connected through the movement of the lithosphere itself. Earth's crust behaves less like a static shell and more like a migrating mosaic, with fragments continuously created, displaced, deformed, and consumed. The ring of fire is the visible outline of that motion. Subduction zones also store enormous mechanical energy. As descending and overriding plates grind against one another, stress accumulates within locked sections of crust. When those sections abruptly rupture, the released energy can reshape coastlines within minutes. In March of 2011, a magnitude 9.1 earthquake struck offshore of northeastern Japan along the Japan Trench, another subduction boundary tied to the broader Pacific system. The sudden displacement of the seafloor launched a tsunami across the Pacific basin. Entire towns disappeared beneath water, moving faster than most aircraft at cruising speed. The event demonstrated that the calm surface of the ocean can conceal forces operating on scales almost beyond ordinary intuition. For many years, scientists believed the Mariana subduction zone behaved somewhat differently from other Pacific trenches. Because the Pacific Plate descends there at an unusually steep angle, the region was considered less likely to produce the largest megathrust earthquakes associated with catastrophic tsunamis elsewhere around the Ring of Fire. That assumption weakened in 2016 when the Mariana region generated a magnitude 7.7 earthquake. The event was not among the largest recorded within the Pacific Basin, yet it reminded researchers that the trench remains active, evolving, and only partially understood. Even now, beneath the darkness west of the Pacific horizon, the plates continue their descent without pause, extending a planetary cycle far older than humanity itself. Far below the familiar layers of the ocean, beneath the reach of storms, whales, and drifting sunlight, the seafloor enters a realm so deep that surface life no longer provides its energy directly. At 6,000 meters, the hadal zone begins. Challenger Deep descends nearly 5,000 meters farther still into conditions that remained untouched for almost all of human history. No sunrise has ever reached this depth. Light vanishes completely long before the trench floor appears. Without sunlight, photosynthesis becomes impossible. There are no forests of kelp, no floating algae blooms, no microscopic phytoplankton turning solar energy into living tissue. The entire ecological structure of the trench depends instead on fragments descending slowly from the distant ocean above. Marine snow drifts continuously through the darkness. Dead plankton, mucus, microscopic shells, fecal pellets, scraps of tissue, and dissolving organic debris sink downward in an almost invisible rain. Some particles take days or weeks to complete the descent. During that journey, countless organisms consume and recycle much of the material. By the time it settles onto the floor of Challenger Deep, little nutritional value remains. Yet even there, life persists. The first layer of that hidden ecosystem exists within the sediment itself. Dense microbial communities inhabit the mud, feeding on whatever organic compounds arrive from above. Bacteria and archaea slowly dismantle fallen material molecule by molecule, extracting traces of chemical energy from what appears, at first glance, almost lifeless. These microorganisms form the foundation of the hadal food web, sustaining larger creatures through processes operating silently beneath the sediment surface. Among the most common visible animals are amphipods, pale crustaceans resembling translucent shrimp. Cameras lowered into Challenger Deep repeatedly record them gathering around any source of organic matter that reaches the trench floor. A dead fish, a drifting fragment of squid, even bait lowered by researchers, can attract swarms numbering in the thousands. In the darkness, chemical traces spread through the water and are detected with extraordinary sensitivity. The amphipods themselves survive pressures that would instantly destroy most shallow water animals. Their cell membranes contain specialized molecules that remain flexible despite compression exceeding 1,000 atmospheres. Proteins inside their bodies are stabilized by compounds known as piezolites, chemicals that prevent essential biological structures from collapsing under immense pressure. Across portions of the trench floor, another life form spreads in astonishing abundance. Xenophyophores, giant single-celled organisms, rest upon the sediment like delicate discs and branching fans. Some grow nearly 20 centimeters across, making them among the largest individual cells ever discovered. Though physically fragile, they thrive in the hadal environment by collecting particles from the surrounding mud and water. Their bodies also create miniature ecosystems. Tiny worms, crustaceans, and microbes inhabit the surfaces and cavities of these enormous cells, turning individual xenophyophores into living habitats scattered across the abyssal plain. Nothing in the hadal zone moves quickly. Energy is too scarce for wasteful motion. Organisms conserve every resource, surviving through patience, chemical efficiency, and adaptations refined across millions of years beneath perpetual darkness. At the bottom of the trench, life does not flourish in abundance as it does near coral reefs or coastal shallows. Instead, it persists quietly, shaped by pressure, isolation, and the slow descent of nourishment from a world impossibly far above. The camera descended for hours through black water before finally settling above the trench floor. Around it drifted fine particles of sediment, moving slowly in the weak currents near the bottom of the Mariana system. Then, out of the darkness, small pale shapes appeared and circled the bait container with quick, fluttering movements, unlike the heavy swimming patterns expected from deep-sea animals. In May of 2017, researchers aboard a Japanese expedition filmed those animals at a depth of 8,178 meters. The footage documented the deepest fish ever observed alive in its natural environment, a species now known as the Mariana snailfish, Pseudoliparus swirei. At first glance, the fish appears almost delicate. Its body is translucent and lightly colored, with skin so thin that parts of its internal anatomy can be seen through the tissue. It possesses no scales and little visible armor. In shallow water, such softness would seem vulnerable. In the hadal depths, it becomes an advantage. Hard structures behave differently under immense compression. Bones and rigid tissues experience intense mechanical stress as pressure rises. The snailfish instead relies on a body built around flexibility. Its skeleton remains lightly mineralized, its tissues gelatinous and compressible. Rather than resisting the pressure directly, the fish exists in near equilibrium with the surrounding water. Its greatest adaptation, however, occurs at the molecular level. Inside every cell, proteins must maintain precise three-dimensional shapes to function correctly. Under pressures exceeding 1,000 atmospheres, those structures begin to deform. Enzymes fold improperly. Biological chemistry destabilizes. For most vertebrates, life simply becomes impossible. The Mariana snailfish survives through unusually high concentrations of trimethylamine oxide, a molecule abbreviated as TMAO. This compound stabilizes proteins and protects cellular machinery against compression. As depth increases, the amount of TMAO inside deep-sea organisms also rises. In snailfish, the concentration reaches extraordinary levels, allowing metabolism and nerve function to continue in conditions that would disable almost any other fish. Researchers believe this adaptation approaches a hard biological limit. Beyond roughly 8,400 to 8,600 meters, enough TMAO would be required that the chemistry of vertebrate tissue itself would become unstable. The snailfish lives remarkably close to that boundary, occupying one of the narrowest physiological margins known among complex animals. Despite its appearance, the fish is not passive. In the sparse ecosystem of the hadal zone, it likely functions as one of the dominant predators. Video observations show it actively hunting amphipods and other small invertebrates across the trench floor. Its movements are efficient and controlled, conserving energy while remaining alert to even faint traces of motion in the sediment. The species also reproduces in total darkness, navigating an environment where visual signals have little meaning. Sensory systems tuned to vibration and chemical detection become more important than sight. Every adaptation reflects the demands of a habitat almost completely isolated from the surface world. The Mariana snailfish exists near the deepest edge of vertebrate possibility, suspended between chemistry and pressure at the floor of the Pacific. It survives not through strength or speed, but through a quiet series of molecular adjustments refined across immense spans of evolutionary time. Long after the visible creatures of the trench disappear into darkness, life continues in forms so small they remain invisible, even when gathered by the millions inside a single spoonful of mud. Beneath the sediment of Challenger Deep, within spaces between mineral grains smaller than dust, entire biological systems operate continuously under pressures that once seemed incompatible with life itself. In 2025, researchers involved in the MIR project completed one of the most detailed biological surveys ever conducted within the Mariana Trench. Sediment cores collected from multiple depths revealed microbial communities unlike anything previously cataloged. Nearly 89.4% of the identified microbial species had never before been described by science. The discovery suggested that the trench does not merely contain isolated deep-sea organisms. It supports an enormous reservoir of biological diversity that remained hidden for almost all of human history. Unlike surface ecosystems, these microbial communities cannot depend on sunlight. No photosynthesis exists in the hadal depths. Instead, the organisms rely on chemosynthesis, extracting energy directly from chemical reactions occurring within the trench environment itself. Hydrogen, methane, sulfur compounds, and chemically altered minerals rise through fractures associated with the subducting Pacific plate. Microbes oxidize these compounds, breaking molecular bonds and harvesting the released energy to construct organic material. In effect, the trench floor operates on geological chemistry rather than solar radiation. This process creates a biological world connected more closely to the planet's interior than to its surface oceans. The sediment itself is densely inhabited. Every gram of mud may contain billions of microbial cells layered through the trench floor in astonishing concentration. Rather than existing sparsely at the bottom of the ocean, microbial life forms a continuous living fabric spread through the hadal sediment. Many of these organisms survive conditions that would rapidly destroy ordinary cellular structures. Under extreme compression, the membranes surrounding most cells become rigid and unstable. Essential transport systems fail, molecular movement slows, life processes collapse. The trench microbes avoid this fate through altered membrane chemistry. Their fatty acid compositions differ significantly from those found in surface organisms, allowing the membranes to remain flexible despite immense pressure. Proteins inside the cells are similarly modified, maintaining functional shapes where ordinary biological molecules would deform or cease operating entirely. Some species also reproduce extraordinarily slowly. In the cold darkness of the trench, energy arrives in limited quantities, and metabolism proceeds at a reduced pace. Cells divide gradually, conserving resources across generations that unfold over spans of time, difficult to observe directly in laboratory conditions. Despite the isolation of the hadal environment, genetic studies reveal remarkable evolutionary complexity. Different depths within the trench host distinct microbial populations adapted to subtle variations in chemistry, pressure, and sediment composition. Even neighboring regions of the trench floor may support communities with dramatically different biological signatures. The Mariana Trench, therefore, contains more than a few extreme organisms surviving at the margins of possibility. It contains a parallel biosphere, sustained by chemical pathways almost entirely independent of the sunlight-driven ecosystems above. Far beneath the waves, beneath the drifting marine snow and the descending tectonic slab, life persists in microscopic abundance, woven invisibly through the sediment of the deepest ocean on Earth, far beneath the trench floor, below the sediment, below the fractures carrying seawater into the crust. The Pacific Plate continues its descent into regions no human instrument can directly observe. Earthquakes provide glimpses of its path, tracing the sinking slab through the mantle like distant flashes inside stone. The plate does not vanish abruptly. Its destruction unfolds slowly, across depths and timescales so immense that continents can rearrange, while the process continues uninterrupted. At the surface, the Pacific Plate appears rigid and stable, yet beneath the Mariana Trench it bends downward and enters the mantle at one of the steepest angles on Earth. Temperatures surrounding the slab rise steadily during descent, climbing from a few hundred degrees Celsius near the upper mantle toward well above 1,000 degrees deeper below. Even then, the plate does not immediately melt. Pressure increases alongside temperature, and under such compression, rock behaves differently from ordinary intuition. The slab remains largely solid while descending through regions hot enough to liquefy similar material at the surface. Minerals deform gradually rather than flowing freely, allowing the plate to preserve its structure far deeper than early geologists once believed possible. Within the crust and upper mantle portion of the slab, minerals contain chemically bound water trapped during millions of years beneath the ocean. As the descending plate reaches depths of roughly 100 to 200 kilometers, pressure and heat destabilize those hydrated minerals. Water is released and forced upward into the mantle above. That migration alters the chemistry of the overlying rock. Melting begins more easily in the hydrated mantle wedge, generating magma that eventually feeds the volcanoes of the Mariana Island arc far overhead. The volcanoes, mud systems, and hydrothermal features near the trench all originate from transformations occurring inside the descending plate itself. Deeper still, the slab encounters boundaries within the mantle where minerals reorganize into denser crystal structures. These phase transitions occur roughly between 400 and 700 kilometers below the surface. Olivine, one of the dominant minerals in the upper mantle, transforms into entirely different forms under the changing conditions. Such transformations affect the slab mechanically. Some regions may stiffen while others weaken. Portions of the descending plate can fracture, buckle, or tear apart as the internal mineral structure reorganizes under extreme pressure. Deep focus earthquakes detected hundreds of kilometers beneath the trench likely result from these continuing stresses within the sinking slab. The deepest seismic signals associated with the Pacific Plate have been recorded at depths approaching 800 kilometers. Beyond that level, the slab becomes increasingly difficult to trace clearly. Many researchers believe portions flatten within the mantle transition zone, spreading laterally rather than descending directly into the deeper mantle below. Yet even there, the material is not truly gone. Over hundreds of millions of years, mantle circulation may gradually remix fragments of the ancient Pacific Plate into the deeper interior of the planet. Eventually, some portion of that material could rise once more through mantle convection beneath distant mid-ocean ridges. There, magma would cool into fresh oceanic crust, beginning another cycle of movement across the seafloor. The rock now sinking beneath the Mariana Trench first formed roughly 180 million years ago in an ancient ocean far from its present location. Since then, it has crossed much of the Pacific Basin, cooled, thickened, fractured, and finally descended back into the earth from which it originally emerged. Long before the Pacific Plate approached the Mariana Trench, it traveled beneath open oceans that no longer exist in their original form. It moved slowly across the planet through ages of shifting climate, volcanic upheaval, biological evolution, and magnetic reversal, carrying within its minerals a layered memory of ancient Earth. Oceanic crust is not inert stone. As seawater seeps through fractures in the rock over millions of years, chemical reactions quietly alter the minerals below. Elements are exchanged between water and basalt. Tiny organisms settle onto the seafloor and become buried within sediment. Volcanic ash from eruptions thousands of kilometers away drifts downward and settles across the plate in thin gray layers. Every stage leaves a trace. That information remains preserved long after the surface world has changed beyond recognition. As the Pacific Plate nears the trench, the archive begins descending into the mantle. Sediments are compressed, minerals deform under immense pressure. Water trapped inside crystal structures remains sealed within the rock until rising temperatures force it outward deep beneath the forearc region. Some of those expelled fluids eventually rise again through the serpentinite mud volcanoes scattered between the trench and the Mariana Islands. The mud these volcanoes release is not ordinary sediment. Mixed within it are fragments of the descending slab itself, pieces of ancient oceanic crust carried upward from deep below the seafloor by alkaline fluids moving through fractures in the overlying plate. Scientists examining these rocks are sometimes handling material that formed during the Jurassic period, when dinosaurs had only recently begun spreading across the continents. Among the fragments are remnants of ancient seamounts that once stood above the Pacific Basin before plate motion carried them toward the trench. Over millions of years, they were pulled downward, fractured apart, and partially buried within the subduction zone. The trench consumes them slowly, Yet in scattered places, it also returns pieces of them back toward the surface. This recycling process allows geologists to reconstruct parts of Pacific Ocean history that would otherwise be permanently lost. Magnetic minerals inside the oceanic crust preserve another form of memory. When molten rock first cooled at ancient spreading ridges, iron-bearing minerals aligned themselves with Earth's magnetic field. Once locked into solid rock, that orientation remained fixed. As Earth's magnetic poles reversed repeatedly over geological time, alternating magnetic patterns were written across the seafloor like stripes. Near the Mariana Trench, some of the oldest surviving sections of Pacific crust still preserve those magnetic signatures. They record the orientation of a planet that looked profoundly different from the modern world. The oldest rocks approaching the trench formed before birds existed, before flowering plants spread across the continents, before the Atlantic Ocean fully opened between drifting landmasses. They preserve chemical traces from seas that washed across Earth nearly 180 million years ago. The Mariana Trench is often described as the deepest place on Earth. In another sense, it is also one of the oldest places still accessible to study, where fragments of vanished oceans continue speaking through stone. Far beneath the surface of the Pacific, the Mariana Trench is performing work that extends far beyond its own darkness. Every year, enormous quantities of water and carbon are drawn downward through the subduction zone, carried into the planet's interior by the descending Pacific plate. The trench is not merely a scar in the seafloor. It is part of a global circulation system operating across geological time. As oceanic crust forms at mid-ocean ridges, seawater seeps into fractures within the hot rock. Chemical reactions alter the minerals inside the crust, trapping water molecules within newly formed hydrated minerals. Layer by layer, the ocean floor becomes saturated with chemically bound water long before it approaches a trench. Sediment resting above the plate also contains water locked within clay minerals and pore spaces between grains. By the time the Pacific plate reaches the Mariana subduction zone, it carries a vast hidden reservoir downward into the mantle. Some of that water is released relatively shallowly, escaping upward through fractures and feeding the mud volcanoes and volcanic arc systems farther west. Yet a significant portion continues descending much deeper into Earth. Minerals stable near the surface become unstable under rising pressure and temperature. Their crystal structures reorganize. Water is squeezed from the rock and forced into surrounding mantle material. In some regions, however, water-bearing minerals remain stable at astonishing depths, transporting water hundreds of kilometers beneath the crust. Over immense spans of time, subduction zones act as one of the primary pathways carrying surface water into Earth's interior. Volcanoes complete the cycle in reverse. Water and gases released from descending slabs contribute to magma formation, and volcanic eruptions gradually return part of that material to the atmosphere and oceans above. The balance between water carried downward and water released upward influences the long-term volume of the oceans themselves. The Mariana Trench participates in a planetary exchange that has operated for billions of years. Carbon dioxide follows a similar path. Marine organisms build shells from dissolved carbon compounds in seawater. When those organisms die, their remains settle onto the seafloor and become incorporated into sediment riding atop the oceanic crust. As the plate descends, carbon-rich minerals are carried downward with it. Some carbon returns through volcanic systems as gas released into the atmosphere. Some may descend much deeper into the mantle and remain stored there for immense periods of time. Subduction zones therefore function as regulators within the long-term carbon cycle, gradually removing and returning carbon over geological ages. Without that balance, Earth's climate history might have unfolded very differently. If oceanic crust were never recycled, the seafloor would continue accumulating indefinitely. Chemical elements exchanged between rock, ocean, and atmosphere would no longer circulate through the same planetary system. Continents would evolve differently. Ocean chemistry would slowly drift away from its present state. The Mariana Trench exists because the planet is active. It bends, fractures, absorbs, releases, and recycles material continuously beneath the sea. In darkness, nearly 11 kilometers below the surface, the trench is quietly connected to coastlines, clouds, volcanoes, rivers, and the chemistry of the air itself, part of a planetary mechanism vast enough to shape the long stability of Earth's living world. The floor of Challenger Deep lies nearly 11 kilometers beneath the Pacific surface, isolated by darkness, pressure, and distance from every familiar environment of human life. For most of history, it seemed unimaginable that anything produced by civilization could ever reach such a place. Yet fragments of modern industry now rest quietly within the sediment there. When Victor Vescovo descended into Challenger Deep in 2019, the plastic bag and candy wrappers observed on the seafloor confirmed what researchers had already begun to suspect through sediment analysis and biological sampling. Human waste had entered even the deepest basin on Earth. The contamination was not limited to large, visible debris. Sediment cores recovered from Challenger Deep contained microplastics distributed throughout the mud, tiny fragments, smaller than 5 millimeters, produced by the breakdown of larger plastics exposed to sunlight, waves, and chemical erosion at the ocean surface. Some particles likely began as discarded bottles, fishing gear, synthetic fabrics, or industrial packaging, drifting through surface currents thousands of kilometers away. Plastic does not remain floating forever. Microscopic algae and bacteria colonize its surface, forming thin biological films that gradually increase its density. Over time, the fragments lose buoyancy and begin sinking through the water column. The descent can take years or decades. During that slow fall, the particles move through layer after layer of ocean life, before eventually settling into trenches and deep basins where currents weaken and sediment accumulates. The Mariana Trench functions partly as a collection point for material descending from above. Animals living there now interact with that pollution directly. Amphipods recovered from hadal depths have been found with plastic particles inside their digestive systems. These scavengers spend their entire existence in perpetual darkness under pressures capable of crushing steel structures at the surface. Yet inside their bodies are fragments manufactured in factories far above the ocean they inhabit. Industrial chemicals have followed a similar path downward. Researchers studying trench organisms discovered high concentrations of persistent organic pollutants, including polychlorinated biphenyls, compounds once widely used in electrical equipment and industrial manufacturing before many nations banned them decades ago. These chemicals resist natural breakdown and accumulate within food webs over time. Remarkably, some amphipods collected from the Mariana Trench contained pollutant concentrations exceeding those measured in heavily industrialized coastal regions. The deep ocean does not isolate itself from the surface world as completely as it once seemed. Instead, material drifts steadily downward, linking distant human activity with ecosystems that evolved in near total separation from sunlight and weather. The contrast is difficult to ignore. The trench itself required nearly 180 million years of tectonic motion to form. Oceanic crust spread outward from ancient ridges, cooled, thickened, fractured, and slowly descended back into the mantle. Entire biological eras passed while the system evolved beneath the Pacific. Industrial civilization altered it within generations. Even so, life persists there. Amphipods continue scavenging across the sediment. Microbial communities remain active within the mud. Snailfish still move through the cold darkness above the trench floor. The Mariana Trench remains one of the most remote environments on Earth. It is also no longer untouched, carrying within its deepest sediment a quiet geological record not only of ancient oceans, but of the brief industrial age now unfolding at the planet's surface. Long after the first sounding lines vanished into Pacific darkness, long after bathyscaphes and robotic landers reached the trench floor, the Mariana system remains only partially understood. The maps have improved. The vessels have improved. The questions have multiplied faster than the answers. Even now, most of the hadal zone has never been directly observed by human eyes or cameras. Vast portions of the trench system remain represented only by sonar shadows and scattered measurements taken during brief expeditions separated by years. Beneath the ocean surface exists a landscape more poorly explored than many planetary bodies orbiting far beyond Earth. The uncertainty extends into biology most of all. Each scientific expedition retrieves sediment crowded with organisms unfamiliar to science. Tiny crustaceans, worms, microbes, gelatinous animals, and soft-bodied invertebrates emerge from traps and sample cores carrying anatomical features that do not match existing classifications. Some organisms degrade before they can even be fully studied, their bodies adapted so specifically to crushing pressure that they collapse or rupture during ascent toward the surface. Genetic sequencing has revealed entire microbial lineages, unlike those known from shallower oceans. Many appear to possess biochemical pathways never previously documented. Researchers continue discovering enzymes capable of functioning under conditions once assumed incompatible with complex biological activity. The deeper the samples come from, the stranger the genetic landscape becomes. Geology remains equally unresolved. Seismic instruments can track the Pacific plate descending into the mantle to depths approaching 800 kilometers, but beyond that boundary, the signals weaken and fragment. Some geophysicists believe the slab stagnates within the mantle transition zone, spreading laterally like a sheet sinking into dense fluid. Others propose that portions continue descending far deeper into the lower mantle, carrying ancient oceanic crust toward regions inaccessible to direct observation. The planet beneath the trench is still partly hidden from science. Questions also remain about the serpentinite mud volcanoes rising through the Mariana Forearc. Their alkaline chemistry, hydrogen-rich fluids, and mineral reactions resemble conditions some researchers associate with the origin of life on early Earth. Within these environments, inorganic chemistry naturally generates compounds used by living systems today. Whether such systems genuinely resemble the cradle from which biology first emerged remains uncertain. The resemblance is compelling, but evidence linking modern serpentinite systems directly to life's beginnings is incomplete. Meanwhile, human influence spreads downward faster than understanding. Microplastics now exist throughout hadal sediments, yet researchers still do not fully know how these particles alter trench ecosystems over long timescales. Microbial communities regulate carbon cycling, nutrient exchange, and organic decomposition within the deep ocean floor. If plastic contamination changes microbial metabolism even slightly, the effects may ripple through chemical systems operating across immense spans of time and depth. Those consequences remain invisible for now. Above the trench, the Pacific plate continues moving westward by centimeters each year. Deep below, the slab sinks almost imperceptibly farther into the mantle, carrying seawater, carbon, and ancient crust into Earth's interior. The process unfolds so slowly that a human lifetime captures only an instant of it. The Mariana Trench often appears timeless from the surface world above. In reality, it is still changing, still descending, still building volcanoes, fracturing rock, feeding unseen ecosystems, and reshaping the planet grain by grain in darkness almost no human has ever witnessed. Far below the reach of sunlight, where pressure folds, steel, and darkness has remained unbroken for millions of years, the Mariana Trench quietly altered one of humanity's oldest assumptions. For much of scientific history, life was understood as a surface phenomenon, dependent on warmth from the sun and energy captured by green cells drifting through illuminated water. The hadal depths revealed another possibility entirely. At the floor of the trench, ecosystems persist without dawn or seasons. No plant grows there. No ray of sunlight penetrates the water column. Yet microbial communities flourish within sediment and hydrothermal systems, building entire food webs from chemistry alone. Hydrogen, methane, sulfur compounds, and minerals rising from Earth's interior become the foundation of living systems. The discovery reshaped astrobiology almost immediately. Worlds once dismissed as frozen and sterile began to appear newly plausible. Attention shifted outward, toward distant oceans hidden beneath ice and rock elsewhere in the solar system. The Mariana Trench became more than an earthly abyss. It became a model. Among the most compelling examples is Europa, one of Jupiter's largest moons. Beneath its fractured shell of ice lies a global ocean containing more liquid water than all of Earth's oceans combined. Sunlight barely reaches the surface there, and none penetrates below the ice. Yet Europa does not rely entirely on solar heat. Jupiter's immense gravity continually flexes the moon's interior, generating tidal heating deep within the rock below the ocean floor. Planetary scientists believe this process may sustain hydrothermal activity on Europa's seabed, much like the volcanic systems associated with Earth's deep ocean trenches and spreading ridges. If chemical-rich vents exist there, they could provide the same kind of energy gradients that sustain microbial ecosystems in Earth's deepest waters. The Mariana Trench offered the first real evidence that such environments might genuinely support life. Another candidate circles Saturn. Enceladus appears small and pale from a distance, but spacecraft observations transformed it into one of the most scientifically important objects in the solar system. Towering plumes of water vapor erupt continuously through fractures near its south pole, spraying material from an underground ocean directly into space. Analysis of those plumes revealed salts, organic compounds, hydrogen gas, and microscopic silica grains formed under conditions associated with hydrothermal reactions. The chemistry strongly suggests interaction between seawater and hot rock beneath the moon's icy crust. In the deep Pacific, similar reactions sustain ecosystems independent from the Sunday. Microbes harvest chemical disequilibrium the way surface plants harvest light. Entire communities organize themselves around invisible flows of energy emerging from the planet below rather than the sky above. The trench demonstrated that biology can adapt to conditions once considered impossible for complex systems. Pressure alone no longer defines a habitable boundary. Darkness no longer excludes the possibility of ecosystems. Even isolation, across immense spans of geological time, does not necessarily prevent life from persisting and diversifying. Each expedition into the Mariana system widened the definition of where living worlds might exist. The deepest ocean on Earth became a bridge between planetary science and biology, between geology and astronomy. In the silent chemistry of the trench floor, scientists found not only unfamiliar organisms, but a new framework for imagining life beyond Earth, hidden beneath ice, waiting in oceans no human has ever seen. Numbers on a geological scale do not behave like ordinary numbers. They stretch beyond instinct, beyond memory, beyond anything the human nervous system evolved to hold comfortably in thought. 180 million years is not simply a duration, it is an accumulation of vanished oceans, extinct ecosystems, drifting continents, and mountains worn down grain by grain into sediment. The Pacific Plate, approaching the Mariana Trench, began as molten rock rising along a mid ocean ridge during the Jurassic period. At that time, the world was arranged differently in almost every imaginable way. The Atlantic Ocean was only beginning to widen between separating land masses. Vast inland seas crossed portions of the continents. Forests were dominated by conifers, cycads, and ferns rather than flowering plants. Many of the animals, now associated with the age of dinosaurs, had not yet appeared. Stegosaurus still belonged to the future. Tyrannosaurus rex was separated from that newly formed seafloor by more than 100 million years of evolution. No bird crossed the sky above the young Pacific crust. No grasslands existed. Mammals remained small, nocturnal creatures moving quietly beneath reptilian giants. The rock now descending beneath the Mariana system formed in that distant world and then began an almost unimaginably slow migration across the Pacific basin. Year after year, century after century, it drifted westward by centimeters. While continents rearranged themselves above, the plate cooled, thickened, fractured, and accumulated sediments from ancient oceans. Microscopic shells settled across it continuously. Volcanic ash drifted downward from eruptions long forgotten. Seawater penetrated deep fractures within the crust, altering minerals chemically and storing water inside the rock itself. Layer after layer of geological history accumulated while the plate moved through darkness beneath changing seas. Civilizations appeared and vanished in less time than the plate traveled a few kilometers. The trench awaiting that crust did not yet exist in its present form. Subduction in the Mariana region likely began more than 50 million years ago, after profound reorganizations of Pacific tectonics altered the balance of the surrounding plates. Since then, the trench has consumed an enormous expanse of seafloor, recycling crust back into the mantle through a process still unfolding today. The scale of material involved is continental. Entire volcanic chains have formed and disappeared during this interval. Ancient seamounts crossed the Pacific, reached the subduction zone, and were dragged downward into Earth's interior. Some fragmented under pressure, some were scraped apart and returned upward through serpentinite mud volcanoes. Most vanished completely beneath the overriding plate. Human history occupies only a thin surface layer atop this much older movement. Modern humans emerged roughly 300,000 years ago, extraordinarily late in the story of the Pacific Plate. Agriculture appeared within only the last few thousand years. Industrial civilization occupies a span so brief that, against trench formation, it resembles a flash of light reflected momentarily across water before disappearing again into darkness. Yet the geological cycle continues, with complete indifference to human timescales. Far below the Pacific surface, the ancient plate still sinks deeper into the mantle, centimeter by centimeter, carrying with it minerals, seawater, carbon, and the chemical memory of vanished oceans. Long after present coastlines have changed beyond recognition, subduction will continue reshaping the basin, building volcanic arcs, consuming crust, and writing new chapters into the slow architecture of the planet. Beneath the Pacific Ocean, the Mariana Trench appears at first like an isolated abyss, a singular wound in the seafloor descending farther than any other place on Earth. Yet the deeper its structure is understood, the less it resembles an anomaly, and the more it resembles a process, one expression of a planetary system that has been operating continuously for billions of years. The trench exists because Earth is not geologically still. Its outer shell is broken into moving plates, drifting slowly across the surface above a convecting mantle. Heat left over from planetary formation, combined with radioactive decay deep inside the interior, drives that movement relentlessly. Oceanic crust forms, spreads outward, cools, thickens, and eventually returns to the mantle through subduction zones like the Mariana System. The trench is one point in an immense cycle of destruction and renewal. Other rocky worlds nearby appear fundamentally different. Mercury cooled early and became largely inactive. Mars retains evidence of ancient volcanoes and tectonic fractures, but its crust no longer recycles itself on a global scale. Venus possesses volcanic activity, yet its surface behaves unlike Earth's shifting mosaic of plates. None of these worlds show the same continuously mobile crust operating across the entire planet. Earth alone appears to maintain this kind of long-term tectonic circulation. That movement influences nearly everything at the surface. Subduction transports water and carbon deep into the mantle, while volcanoes return portions of those materials back into the atmosphere and ocean. Over immense spans of time, the balance between burial and release stabilizes planetary chemistry. Oceans persist, continents evolve. Atmospheric carbon dioxide fluctuates within ranges that allow liquid water to remain stable at the surface. Without that recycling, Earth may have become unrecognizable long ago. The Mariana Trench is among the clearest visible expressions of this planetary metabolism. There, ancient seafloor bends downward and disappears beneath another plate, carrying sediments, seawater, carbon compounds, and altered minerals back into the interior. The process resembles erosion only in the broadest sense. Entire sections of oceanic crust descend into darkness and pressure over millions of years, becoming part of Earth's interior once again. Nothing within the trench exists independently from the rest of the planet. Its volcanic arcs arise from fluids released by descending crust. Its mud volcanoes depend upon chemical reactions deep below the seafloor. Its ecosystems survive because tectonic activity supplies chemical energy and nutrients. Even the extraordinary pressures within Challenger Deep are ultimately consequences of planetary structure, gravity, ocean volume, and crustal motion interacting together over geological time. The trench is not separate from Earth's living systems. It helps sustain them. Seen this way, the Mariana System becomes less like a remote frontier and more like an organ within a larger body, participating continuously in cycles older than complex life itself. The abyss is severe, but not chaotic. Every fracture, every volcanic vent, every descending slab follows physical laws that have governed the planet since its earliest formation. Far beneath Challenger Deep, the Pacific Plate continues sinking slowly into the mantle, carrying with it the mineral memory of vanished oceans and extinct worlds. The motion is almost immeasurably gradual, yet it never fully stops. Earth continues rebuilding itself in darkness, deep below the quiet surface waters of the Western Pacific. Somewhere beneath the western Pacific tonight, far below shipping routes and weather systems and moonlit waves, the Mariana Trench continues descending into darkness exactly as it did before human history began. Nothing about it pauses for observation. The plate still bends. The mantle still receives ancient crust. Sediment still drifts downward through 11 kilometers of water toward a floor no sunrise has ever touched. And life remains there. Not fragile life, clinging temporarily to an impossible environment, but organisms shaped specifically by it, generation after generation, across spans of time so large they dissolve ordinary human perspective. Their biology belongs completely to pressure, darkness, cold, and chemical energy rising from the earth below. The conditions that appear hostile from the surface are the very conditions that made those ecosystems possible. In the hadal depths, there is no concept of day or night. No season passes across the trench floor. No wind disturbs the sediment. The nearest sunlight exists kilometers overhead, beyond a column of water so immense that it behaves almost like another atmosphere layered above the abyss. Yet the trench is not silent in a biological sense. Microbes continue metabolizing within the mud. Amphipods sweep across the sediment, searching for organic particles drifting down from distant surface waters. Snailfish move through darkness at the edge of vertebrate possibility. Chemical reactions deep inside the planet sustain systems entirely detached from the familiar rhythms of the world above. The Mariana Trench reveals something profound about Earth itself. Life does not merely tolerate the planet's extremes. Over immense spans of evolutionary time, life enters them, adapts to them, and becomes inseparable from them. Meanwhile, the geological engine continues operating beneath everything. The Pacific Plate still sinks gradually into the mantle, carrying minerals formed in vanished oceans long before humanity existed. Water bound inside ancient crust continues descending toward regions of heat and pressure beyond direct reach. Volcanoes continue forming because of processes unfolding far below the trench floor. The cycle remains active, continuous, and indifferent to whether anyone witnesses it. Human civilization occupies only a brief interval within that motion. Cities rise and disappear. Languages emerge and vanish. Entire cultures unfold within spans of time, smaller than a minor geological adjustment along the trench wall. Even the deepest human dives represent only fleeting visits to a process operating across tens of millions of years. And still, despite that scale, humanity learned the trench exists. That knowledge changed something fundamental. It revealed that Earth contains environments more alien than many once imagined possible on our own planet. It showed that darkness does not prevent ecosystems from forming, that crushing pressure does not prohibit complexity, and that the boundaries humans once placed around life were far too narrow. The trench remains distant from ordinary experience, hidden beneath enormous depths of water, and almost entirely inaccessible without extraordinary technology. Yet simply knowing it is there alters the shape of the world in the mind. At the bottom of the Pacific Ocean, beyond sunlight, beneath mountains of water and layers of ancient sediment, the planet continues its slow work in darkness. Rock descends, chemistry shifts. Microbes feed. Tiny creatures move across pale mud, and in that immense cold abyss, life endures quietly beneath the weight of the earth itself.